Thanks, Cyril and Jess, for inviting me to speak here. It makes a nice change from speaking to TV audiences. Really pleased to be here to talk to you about what we're doing with AWS and Bttv. It's early days, but it's very interesting already. I lead a team of solution architects at Bttv. And we recently started on a journey where we're taking our very complex backend and starting to see how we can simplify that. And cloud is a very important part of that. In terms of what I'll speak about today, I'll just give you a little bit of background of TV at BT, and then focus on why Elasticity is so relevant to TV. Talk a bit about what AWS options are available for high elasticity. And you can probably guess I was going to end up talking about Lambda at some point. So I'll focus then on elasticity of Lambda specifically. And then I'll just illustrate some of the things I'm talking about with a concrete example of something we actually built. So BTTV. I'm not going to spend too much time on this, but what you need to know really is we have two sort of classes of products. One is purely about TV, and there we have a set-top box and a whole bunch of apps for various devices, iOS, Android, and web, and more coming on Fire Stick, and Apple TV, and a few others. And then we've got the sport app, which is probably more popular. I met a few people in the bar downstairs who had used the sport app. The thing about these two is in the back end, they are both very different. They're completely separate, independent implementations. The sport app is all in AWS, and the back end for TV is pretty much on our own VMs running on our own tin in our data centers. Over time, our estate has grown and grown, and we have thousands of VMs to manage. And it's really painful managing all those VMs in line with BT security policy. They're effectively treated as pets, not cattle, which is the opposite of what AWS advocate. So it is a very expensive operational overhead. On the other side, with BT Sport, at least we're in the cloud, we're doing AWS, that's great. But it's very much focused on high availability, making sure it doesn't go wrong, because you don't want things to go wrong on BT Sport when there's the Champions League final on. And so there's been less focus on cost optimization. So right now, it is not the most efficient use of the cloud. And so we started to think, well, if we're going to start building things in the cloud for our TV app, can we start to learn from how we can have done things better in sports, and then eventually port those ideas onto sport as well. So essentially, this is a snapshot of our kind of drive to change the way we work. Microservices are in there, continuous delivery are in there, and cloud platform as services as a key part of that, partly because we believe it will enable us to reduce our operational costs, but also because we can just work faster, we can get things done more quickly. And also because we think if we get it right, we will benefit from the elasticity of the cloud. Why elasticity for TV? Why am I so obsessed with elasticity for TV? All you have to do is look at traffic patterns for TV. This is an example of what a typical linear sort of schedule might look like, right? So believe it or not, probably in this room, most people watch on-demand TV, but the vast majority of people still watch linear TV, particularly if there's live events on or the latest episode of Game of Thrones is going to be on tonight. Everyone's going to tune in to watch at that time. So you have very, very, very high peaks centered around typically hourly intervals or half-hourly intervals, and then not much happening in between. It gets worse if you start to introduce some notion of automation. So whereas on the previous slide, that could have been people tuning into a channel, if you had recordings, where recordings are going to start exactly at 7 o'clock, then you have more pronounced peaks. You've got higher peaks and bigger gaps in between the peaks. And then you've got the big live events, where sometimes there's no traffic at all, no one's watching anything, and then a big game's coming up, and all of a sudden you have this massive ramp up. And you can go from a few thousand streams to 600,000 streams in the space of a few minutes. And then to make it even worse, you've got halftime in the middle. So not only have you had to ramp up, but then in the middle, people have to do that, and then you have to ramp up again. So it's really exhausting work for the, if you are trying to provision and deprovision to try and tailor your resources to what the demand is. So why am I bringing all these up? It's, the first thing, that people do with cloud when they're learning is you learn EC2 and you learn autoscaling. And you learn autoscaling is great. It gives you elastic computing. You only, pay for what you want. It automatically ramps up and ramps down. But the problem with EC2 is you always pay for an hour, right? First of all, you have to start scaling up before you need the capacity. And there's always going to be some error in that. You probably end up scaling up too early because you want to play it safe. And then, if I go back to that, what are you going to do? Scale up and down and up and down? It doesn't make any sense because you're paying for an hour anyway. You may as well keep your resource for an hour. And by the time your hour is up, you need it again, right? So EC2 and autoscaling is not elastic enough. And this gives us the notion that perhaps there are different degrees of elasticity, that some things can be more elastic than others. And EC2 and autoscaling is not elastic enough, certainly not for TV. So we need something more elastic. So we need this notion of measuring elasticity, how elastic something is. And I looked around to see, has anyone done any work on measuring elasticity? I just found a few definitions, Wikipedia, a few papers, academic type of papers, which are essentially focusing on the amount of time for which the resource that is provisioned matches the demand you have and how precisely it matches it. For me, these two definitions have something missing, though. There's nothing about paying. I don't really care about what capacity is provisioned. I care about what capacity I'm paying for, right? So if I have deprovisioned an EC2 instance, but I'm still paying for it, that's no good, right? So I'd rather define elasticity in terms of the extent to which paid for capacity exactly matches the demand that I've got. And with a definition, you can then think about, at one extreme, the completely inelastic case, and on the other extreme, the perfectly elastic case. With the inelastic case, the orange line there is how much capacity you have. It's always fixed, right? So that might be an EC2 instance that I've spun up, and it's just there. It's just one instance, and it never changes. Demand ramps up. For a while, I've got more capacity than I need. Then I go over the line, and I don't have enough capacity, right? That's no good. That's the inelastic extreme. The perfect extreme on the right is heaven, right? I'm only paying exactly for the resource that I need. I have not found yet a platform that can do that, right? But what we can do is look for platforms that come close to that. So most platforms that came to be elastic, or all platforms that came to elastic, are somewhere in the middle there. And it's a case of, can we find something that's closer to the graph on the right than to the graph on the left? Yeah?
AWS have recently changed their EC2 billing policy, so now you can get
10 minutes.
Second billing.
Oh, right.
On Linux.
I didn't.
Is that correct?
Yeah, next month, as of the 4th of October.
As the 4th of October.
Right. So that's great news. That's great news. Okay. Okay. But it's still, you still have to pay for a whole VM, though. I don't, So I mean, yeah, that's great that that's happening. You still have to think about when you scale up. You tend to have to want to scale up a bit earlier than when you need it, because you need a bit of margin of safety. But it is good that it's heading in that direction. That's great news. Okay. The trouble with AWS is it's changing so fast, I can't keep up. Elasticity is not the same as scalability. So scalability is purely about the ability of the system's potential to be enlarged to accommodate growth. You can achieve that just by over-provisioning, right? It's nothing to do with elasticity. Right? What are the characteristics that determine elasticity? There are two key characteristics. One is how quickly can you adapt to change, right? So it's the timeliness of adaptation to changes in demand. If you adapt too early, you're paying for capacity that you're not using. If you adapt too late, then you're having to throttle requests and turn demand away. But it's not just about the timeliness, it's also about the granularity of adaptation. So when I do need to increase or decrease, what is the chunk, what is the smallest chunk of resource that I can add or subtract from my current pool? And that's essentially the resource provisioning unit size. over-provisioning is just as inelastic as under-provisioning, right? Just as early scale-up is just as bad as late scale-up. So essentially, those are the two sort of characteristics depicted on the graph there. So with these kind of measures, we can sort of try and plot various AWS compute platforms with those two axes. I think even with the news that you can now do billing per second, it remains the case that with those measures, Lambda would be right at the top right corner in terms of timeliness of adaptation and granularity of adaptation. You can't get better than just getting 1 to 8 meg of a memory-based platform for 100 milliseconds. You can't get much finer grain than that. So is Lambda the ultimate elastic compute platform? And can we use Lambda to address some of the issues we can see in TV demand? So considerations for Lambda. If we talk about granularity of adaptation first, essentially resources charged in units of megabyte milliseconds, right? You can get, the smallest thing you can get is 128 meg for 100 milliseconds. You can increase that in chunks of 64 meg up to 1536, and 100 milliseconds up to a maximum of 300 seconds. So very, very granular in terms of the resource not just in terms of memory, but also the time for which you need to pay, right? So I don't think we have any problems there. We're happy with that. But what about timeliness of adaptation? You've got container initialization time, cold start, which used to be quite an issue. For us, the real worry is scaling out to very high volumes. So there are limits. So Lambda will scale up very, very nicely and very quickly up to a point. But when you hit that point, then it starts to get a bit trickier. So we'll explore that in a second. Also, you've got multiple functions running in the same account. There is a danger that if you ramp some up to very high volumes, right? But if you start to hit throttling limits there, then other functions could also suffer. There's no way to partition capacity so that some functions are protected from others, unless you separate into different regions or different accounts, which is a bit of a faff. Specific to Lambda as well, there's issues around execution consistency and trade-offs between memory size and execution time. So let's start with consistency. This is a little test here. Just a Lambda that just returns a response. Very simple. You can immediately see that as you add more memory size, you get more consistent behavior. So the different bars here are executing this function at different memory sizes, 128, 256, 512, etc. Essentially, what I did here was this function ran every minute for about 5 days. And we plotted this, and you can see that if you want consistent under 20 millisecond performance, the higher memory sizes will give you that. So there's a link between the two. Another test here is doing something a bit more significant. This is writing to a DynamoDB database. I should call out, there's obviously the factor of the delay of the DynamoDB database itself, which can also affect the results here. But broadly, again, you can see obviously, this function takes a bit longer to execute, but again, you get more consistent performance at higher memory. It's worth calling out that the trade-off between memory size and execution time. On the one hand, for under 100 milliseconds, I could choose the 512, and I'd get close to 100% of my cores under 100 milliseconds. So I'm paying more for 512 than I would for 256. But for 256, I'm only going to get 50% of my cores under 100 milliseconds. And for the others, I'm going to have to pay for 200 milliseconds, and therefore I'm going to have to pay more for those 256s anyway. So even from a cost perspective, memory sizes that are higher can sometimes end up being cheaper. So this has given us a kind of a vehicle for testing different functions and seeing what's the optimal what's the sweet spot, if you like, for the memory size for each function. And that really has to be worked out on a function-by-function basis. What about container reuse and cold starts? This used to be a problem. There are some old articles on AWS talking about frequent cold starts. So I wanted to check, because I read more recent articles saying, oh, cold starts are no longer a problem. They've all gone away. This is a Node.js. This is a simple function that simply counts how many times a container is reused. So I'm just using a global variable to count how many times the container is reused. I'm just creating a container ID by using the current date at the time the container is initialized. And I log, every invocation is logged with the count, and I increase the count every time. And interestingly, what came out of that was that, sometimes I had runs. This was run every minute for 3 days. I had runs of 493 minutes using the same container. The number of code starts every 3 days was only around 17 in the worst case. So code starts don't happen that frequently, and not worth worrying about, at least for this size of function. Also, the mean duration of code starts was not that much worse than the mean duration for all calls. In fact, in one case, the all calls was worse than the mean duration for code starts. And you can see that the percentage of calls where the mean was greater than the mean for code start was actually quite low, right? So I'll just show you this. This is one of the traces of the functions there at 1024. Code start was only 4 milliseconds, but some of the warm ones were actually higher, as much as 20. So we don't worry about code starts. We just think that's not really an issue. What is more of an issue is scaling out. This is an extract from the documentation from AWS Lambda on scaling on concurrent execution. Essentially, you always can get up to 1,000, right? So we have to separate the safety limit from the capacity limit, right? Everyone starts with a safety limit of 1,000. You can't have more than 1,000 Lambda functions. You can ask Amazon to increase that for you. But increasing that does not mean you have that capacity right away. What you will get right away is region dependent. So in the big regions, like in Ireland, for example, you will immediately get 3,000 concurrent executions, as long as your safety limit has been increased to at least 3,000. For all other regions, you only get 1,000 to start with. Thereafter, if you hit those limits and you start throttling, AWS will add executions at the rate of 500 per minute, right? So you can go from 3,000 to 3,500 after a minute, to 4,000 after another minute, etc. So the question is the ramp up of that additional capacity going to be fast enough for our needs? Essentially, the number of containers we need, which I've sort of got a little formula here, it's quite straightforward. The number of containers I need depends on two things. A, how long it takes for the functions to execute, and B, how quickly the actual invocation rate, the number of transactions per second I need to meet, right? Unsurprisingly, the shorter the time for the function to execute, the more the same container can be reused, so that within a second, I can get more executions from one container. So for example, if I had a time of 50 milliseconds and a rate of 2,000 transactions per second, I would need 100 containers, etc. So it's in our interest to keep n to a minimum, the number of containers to a minimum, by keeping the execution time to a minimum, and by keeping the rate of invocation to a minimum. So how can we do that? To lower Lambda execution time, we've already talked about trading off memory size and execution time. If you use a higher memory size, you will get a faster execution time on average. Don't use VPCs if you can avoid VPCs, because they add code start time. So that's one thing I should have said on code starts, is that experiment had no VPCs, right? That was just usual Lambda outside VPC. We haven't seen VPCs add a significant start to code start time. If you're using Dynamo, if you're writing state to Dynamo, then use DAX if you have an application where you're likely to get a high hit rate. It doesn't always happen. It's not always the case that DAX will help you. It depends on the application. You could replace DynamoDB with Elasticache. It certainly improves performance a lot and reduces that execution time significantly. Only problem is Elasticache, despite its name, is not really that elastic. And perhaps another conversation for another day is around the elasticity of databases and storage. But that's another talk. I think the two really key ones for me, which I'll touch on in the example I'm going to give, is conditional writes can save you a read. Instead of reading from the database and then writing an update, just write right away with a conditional write. We'll see an example in a second. And the real important one is go asynchronous. So if you go asynchronous and you can return from that Lambda as quickly as possible and then leave as much processing as possible to happen asynchronously, that will reduce the time taken for that Lambda to execute. So what about lowering the rate of requests? If the requests are being driven by customers hitting a button, hitting a play button, for example, there's not much you can do about that, right? You can't alter customer behavior. However, what we do often see in TV applications is that you have periodic repeats. So typically, a user will do something which triggers a request. And then after that, there will be regular requests, say, every half a minute, for example, which are all relative to that first request the customer made. And that means that if you had a big peak at a certain point in time, that peak is going to repeat itself over and over and over again. And when you combine that with new requests coinciding with repeat requests from previous customers, and they all combine, you start to get this pattern of growing peaks. So you can't change when the user hits the play button, but what you can do is vary the period between those repeated calls to try and smooth out some of those peaks and then end up with something like that, right? So by doing that, it's helped a bit. You've now reduced the number of requests per second by a certain amount. This is just a noddy example, but you could, if you get it right, you could reduce that even further. So I'd just like to finish off with an illustration with a real-life service. So this is a sort of diagrammatic representation of a microservice for managing streams. So what this does, this stream manager service in the middle, is essentially it keeps track of who's playing what, how many streams any customer has ongoing at any one time. It's used for a number of purposes. One, we limit the number of streams a customer can have at any point in time. So for example, if within a household there are 5 devices, we would only allow 2 of those devices to stream certain content to those devices at the same time. So we need to be able to track how many concurrent sessions there are on a per account basis. We also have need to be able to communicate, to know what the client is doing, to know the client is still alive, to be able to communicate with the client and send messages to the client. So the idea here is the client starts, on the right-hand side we've got the client player. When the customer wants to play video, they send a play request to a playback service. That playback service does a number of checks. Is the customer entitled to watch this content? Are they in the UK? And a whole bunch of other checks. And one of those checks would be, is there a concurrency limit on this content? And if so, is the customer within their limit? If all those checks pass, the playback service will then create a stream in the stream manager service. And after that, a handle will be returned back to the client. And after that, the client will send periodic heartbeats every 30 seconds to the stream manager to say, I'm still here, I'm still streaming. That heartbeat gives us an opportunity as well to send an action back to the client. So if operations decide they want to send a message to the client, they can lodge that with the stream manager service. The next time a heartbeat comes in, the stream manager service can say, hey, I've got an action for you, and pass it back in the response. That action might be something like a force terminate. I want to force terminate the customer stream because I think they're a pirate, for example. Or I want to display a message on the customer's screen, or I want to tell them, send them a notification midway to them watching their video that something of interest has happened. So there's a back channel there for essentially sending things back to the client. If a client disappears because their batteries run out, whatever, we need to be able to tidy up the state in the stream manager service. So we've got this periodic cleanup, which is periodically looking for sessions which haven't had a heartbeat for a while and cleaning them up. And then finally, we've got event reporting so that we know what's going on, essentially. So how would we build this in Lambda? Oh, before I do that, the non-functionals around this typically would be something like this. So the blue line here is new plays, right? As more plays are added, every 30 seconds, each play means there's going to be a heartbeat 30 seconds after that, and after that, and after that. So that orange line is showing the heartbeats and the growth in the heartbeats, and the green line is the sum of the heartbeats and the plays. So that's your total requests. And what we'd like to do is be able to support, in the order of 50,000 transactions per second using Lambda. This could get bigger. So the obvious way to build this, or the simplest way to build this, is you have, so the stream manager is the blue box in the middle, right? So you've got a client that talks to API gateway. In this particular example, the play function is implemented on EC2. That could become a Lambda as well, but for now it's EC2, it's VMs. So the client does the play there. That does all the play checks, etc., all that mission control. That mission control says, yes, go ahead. It talks to the Lambda to say, yeah, create a session for this client. Returns. And subsequently, the client starts to send heartbeats through the client gateway to that Lambda function. That Lambda function stores its state in a Dynamo DB database. Typically, for every heartbeat, it needs to do a read first and then a write. So it does a read to check whether there's any client actions pending for that client. And then it does a write to update the timestamp to say this is the last time the client contacted the service. So there's a read and a write. On the other side, you've got another Lambda here for the operations and sort of help desk type people to be able to look at what's going in the database, possibly lodge a client action if we want to send an action to the client. And then the periodic housekeeping, cleaning up stale sessions triggered off a CloudWatch sort of timer. So that's the obvious way to do it. The trouble with this is it's completely synchronous. It's simple. But we need to find a way of reducing the time it takes to execute these heartbeats, and also to try and get rid of this very sort of rigid periodic 30-second interval. You could achieve that by randomizing the interval a bit in the client, but there's other things we can do on the server side as well. The first thing I want to talk about is the conditional write. So instead of reading and writing, in the first instance, we might have implemented it as read item, check for pending client action, then write the item, and then return the client action, if present, back to the client. We can replace that with just conditionally write the item, but make the condition such that you say only write if there's no pending client action for the client. So essentially in the code, what you do is you'd include a condition expression here saying client action equals none, right? And write will only work if there is no pending client action. If there is a pending client action, the write will fail. You will then have to read the item to obtain the client action and then rewrite the item. In that case, you're doing 3 Dynamo transactions, which is worse than the 2 we had before, but that happens very rarely, right? In most cases, you're only having to do 1 conditional write. That would probably cover more than 99.9% of the cases, right? So we've been able to replace 2 database transactions with 1 for the vast majority of calls. That made a big difference. The next thing is go asynchronous. So the immediate thing about people think when, the sort of standard AWS architect course is use SQS to decouple your components and make it asynchronous. The trouble is if you put SQS here, so what we're saying here is from API gateway, the play call is the same, but instead of sending a heartbeat to the Lambda, you instead post a message into an SQS queue. You can do that directly from API gateway. And then you have a Lambda that the Lambda periodically polls and checks for messages and pulls the heartbeats in and can process multiple heartbeats at once. So, that will help to reduce your Lambda execution time overall. And it also helps to smooth out those regular peaks a bit because you've got that queue buffering those sort of peaks in the middle. The only problem is we've lost our back channel. There's no way to return a client action back to the client here, right? Because if this guy here lodges an action there, this is only being able to write into the database. If it's read an action, it has no way to go back to the client, to give it back to the client. So a modification of that is have the heartbeat call the Lambda, do a sync read just to check for the action, then launch an async write by posting a message into SQS and return immediately. So here we've got a synchronous read with an asynchronous write. So this means we get our back channel back. This means we're able to return an action back to the client. And it means we've offloaded the more expensive write operation into a queue, which can be dealt with asynchronously. So this helps. But I think where we really want to get to, and this is something we haven't tried yet, is go fully asynchronous in both directions. And this is something we'd really like to explore, where we replace API gateway with IoT gateway and treat these client apps as if almost they were just things, right? And what this enables us to do is we can now send heartbeats, stick them in a Kinesis heartbeat queue, have Lambdas processing these heartbeats from the queue and writing into database. That bit there doesn't give us a back channel, but with IoT using WebSockets, we can actually send messages from server side back to the client directly. So we don't need that synchronous REST type of call anymore. So this would give us full asynchronicity in both directions and should be able to help us minimize the Lambda execution time, get it down to the bare minimum. One last thing I wanted to touch on was, I've been to various forums and seen various websites talking about pre-warming. I don't think it works. I know AWS people don't like it. I mean, the idea here is that if you need to scale out more than the 3,000 that Ireland gives you, and you need that capacity to be there quickly, before your anticipated demand, before your football match starts, you can start to run some Lambda functions sort of to start warming up this capacity. But the thing is, right, you have to, as a minimum, you have to execute all these concurrent functions. You have to do them exactly at the same time, right? And you'd have to be adding 500 every minute to get until you got to the desired point. Amazon say nothing in their documentation and through their support about how long they will keep those containers for you, right? So even though we saw containers being kept for a long time for repeated calls earlier, that is just an experiment we did. It's not backed by Amazon specifications. AWS will not guarantee anything about how long containers will be kept for. And particularly when you scale to high volumes, we could start to see that containers get claimed back a lot more quickly, which makes it harder to pre-warm because you're trying to pre-warm, but it's recycling containers. If you do a lot of pre-warming, it can get very expensive because you're having to make those repeat calls every minute, increasing the number of calls you're making all the time. And that sort of, grows in that fashion. The higher you need to get to, the worse it gets. So we don't like this, and we really want to avoid this. So to recap, is Lambda the ultimate elastic platform from a TV perspective? We think it is up to a region-dependent limit. Certainly for TV, we will have to work with the larger regions. Beyond that limit, rate of ramp-up does become a critical factor. So we need to find ways to reduce our ramp-up rate and doing that by reducing execution time and going asynchronous. For us at BT, what this has meant really is, we've put a lot of thought into how we organize our landing zone, our cloud governance, or our pipeline, but equally we need to put just as much attention, if not more, into how we architect our actual TV services because, you have to design your service for the cloud. You can't just lift and shift what you had on a VM. You really have to think very carefully about how you make best use of the cloud to optimize your costs and your performance. And the third thing, and this has come about both by looking at documentation and talking to Amazon support, and it's not a criticism of Amazon support, they're great, but there's a deliberate vagueness sometimes in places in the documentation because Amazon needs the flexibility to change the way they do things. They will not give guarantees about container recycling. They will not give guarantees about exactly when things will ramp up. And that's because they want the flexibility to experiment with different algorithms for doing that. So that's something we just have to live with. So a good example of a question, we'd really like an answer to is, if you have this is another example of a hard beat and play situation. The green line is the sum of the orange line and the blue line. It's the green line that's of interest here. It's the number of transactions per second. So as soon as, in this example, we're managing to do 10 transactions per second per Lambda container. So we can do 30,000 transactions per second within the 3,000 that Amazon give us in Ireland. As soon as we hit the green line, that triggers an increase of 500 within a minute, 500 Lambdas within a minute, or in our case, 5,000 extra transactions within a minute. If a minute passes, we've lost that bit of, that green bit there, that's all throttled, right? So we've got that, the area under here represents the amount of requests that have been throttled. We don't know exactly when that extra 500 becomes available. The documentation just says you will get 500 extra Lambdas within a minute. If that line were to be shifted there at the start of your minute, then we're okay. If it happens in the middle of your minute, or it builds up gradually over the minute, then that's better, right? But the spec doesn't say. And so on and so on. You've got this, as you ramp up, you've got this continuous problem of having a few functions being throttled. So I have to finish off with a wish list then, to take serverless to the next level. This is serverless at massive scale, right? Wouldn't it be great if we could, be able to guarantee capacity on a per function basis? So first of all, we want to be able to protect critical Lambda functions from other perhaps less critical Lambda functions. I don't mind if a few of my heartbeats are throttled, but if my operations can't get at the console because their Lambda cores are failing, that's a problem. So why can't I protect my ops Lambdas from the heartbeat Lambdas? That would be a really good feature to have. Another good feature to have would be to be able to pre-book capacity for periods in advance. So in a way, a bit like reserved instances with EC2, but do it at a function basis instead. Another nice thing would be if we could prioritize resources so that cores to sensitive functions are less likely to be throttled than cores to non-sensitive functions. So in the example I had earlier, right, with a play call, you need to get back to the customer quickly. They want to play video. It needs to come back right away. A heartbeat, it doesn't matter if it's throttled. It doesn't matter if there's a bit of delay or if the client has to resubmit the heartbeat. So it would be nice if there was contention, the more sensitive functions get serviced first. And then some control over the timing for provision of additional capacity. So back to that graph I showed you here, could we have some control over when that increase happens rather than just leave it to, just trust Lambda to do it for us at the right time. So that's really all I want to talk about. There's some useful articles. I can share these slides, some useful reading there. Thank you. Lambda's great for TV. Any questions?
Thank you very much, Mike. We've got one question over there, and my mic doesn't work. Oh, yeah. Where are you?
Hiya.
Hi.
If you're running all your Lambdas outside of VPC, how's that in terms of control over your data?
Good question. We're relying totally on IAM. That's what we're doing. Now, it all really comes down to what is the data you're managing. For this particular example, the data is stream data. It's completely anonymous. If someone got hold of it, it wouldn't really mean much to them, right? There are situations where we'd need tighter security, and then VPCs would be appropriate. Right. Yeah. But yeah, it's a good point. Yeah. Mm-hmm.
Do we have another question? Yep.
Yeah.
So just you're kicking the tires of the kind of the further extent of Lambda.
Yeah.
I presume you've spoken to Amazon about this.
Yes.
What's their response to your suggestions, conversations, questions?
So some stuff is under NDA, so I can't say. I think what I would say is some of the things I've raised have been raised by many others before. It's not new to them. They hear this all the time. They say the Lambda product team want to keep Lambda as simple as possible and minimize the number of knobs and levers they offer for people to control. I can see why they do that. But I do think at the same time is when you start to get to real large scale deployments, you start to need that little bit extra control. I mean, we don't want too many knobs, right, and to twiddle. We just want the bare minimum. But we do need a bit of reassurance that we're going to have the capacity we need when we need it. I do think they listen, though. You know, and I mean, in some cases, you know, they are acting on the feedback we've given them and others have given them. And, you know, there may be developments, this reInvent coming up, who knows, right? I mean, yeah.
I think that's a perfect transition, Mike, because you just offered me a way to say that our next meetup will actually be a reInvent special on the 6th of December. But thank you very much for the talk.
Thank you. Thank you. Okay. Thank you.
If you've got time, there's probably more questions in the audience. That'd be great to have you on board to have some drinks and some food afterwards.
Yeah, I'll be in the bar, so come in to talk. Yeah, fine.
Mike,
I can take some more now if you or do you want to close?
We might need to run the raffle and close, but we still have the venue downstairs.
Yeah.
And Mike will be in the bar, so that's perfect. So yes, we actually have a raffle for those who participated. There's an Amazon Echo Dot to win. I just need a neutral hand. Here's my neutral hand. It's for my company. Neutral hand, neutral hand. That's what you're supposed to win. Now we've got neutral hand behind it. You're not very neutral, Jazz. All right. Thank you. Brian Byrne. Oh. Congratulations. That was for an amazing question on the first talk. Well, so as I just said, the next meetup will be on the 6th of December. We'll have a reInvent special talking about what happened in Vegas, even though it's supposed to stay in Vegas. And RSVPs are open now, says Ijaz, so go and sign up. Thank you very much for joining us. Thank you to Mike and Max. And we'll see you downstairs for the food, which hopefully has arrived. All right. Thank you.